Now we're going to get into the topics in Chapter 5. And the first topic is reviewing processes that are reversible and processes that are irreversible. I'm going to try to take you through some mental exercises because I think there are some things that I will propose that you know in your mind are just absolutely impossible. Okay. And so what I'm going to try to do is mix the ideas of what's reversible and irreversible with what's possible and impossible. And a lot of the reasons that certain things that you know of that are impossible is the reason that certain things cannot simply be reversed in your mind and in reality. So let's see, what do you figure is the difference between a reversible process going from state A to state B and an irreversible process going from state A to state B? What do you figure is the difference between those two? That's the topic. Okay, well, let's see if we can define a reversible process for thermodynamics class. So it says a reversible process can be reversed without leaving any trace on the surroundings. And that is a good definition. That's a good working definition for what a reversible process is. And so you can see the little example of, here's a closed system at some starting point. It goes to state 2, and the process could be considered reversible if you do exactly the opposite of what you did from 1 to 2, and you go back to state 1, right? So that would be, hopefully that'll give you an idea. That gives you an idea of what is a reversible process. And so it says all real world processes are irreversible. It says so on the slide. I clipped this out of something off the internet. It says, but my claim is that many real world processes can be considered nearly reversible. And so don't get the idea that we're going to study reversible processes for no reason at all, that, all real world processes are irreversible. Do get comfortable with the fact there are many, many real world processes that we could model as nearly reversible. Okay, and so now let's try to define an irreversible process. Well, we said a reversible process can be reversed without leaving any trace on the surroundings. And so therefore, an irreversible process leaves some type of effect on the surroundings. Okay, and so that's the key thing to recognize is when you're identifying an irreversible process, some type of effect is left on the system and or the surroundings. Okay, I'm going to try to take you through a mental exercise of how you might build a reversible process. And so let's start with a closed system. Let's have a piston and cylinder. Let's fully insulate the piston and cylinder, fully insulated, so there's no heat transfer into or out of the closed system or into or out of the surroundings. So that's a key in our little mental exercise. And another thing we're going to say is the piston and cylinder are frictionless. There's no friction between the piston and cylinder, and the process occurs slowly enough so we can consider it quasi-equilibrium. So how could we go about building something where the initial and the final states are identical and there's been no effect visible on the surroundings? Here's what we'll do. We're going to start with a stack of very thin plates on top of the piston. And we're going to slide one plate off. And you see, if you slide one plate off, the piston's going to go up a little bit, right? Because the pressure drops a little bit. And it went up a little bit. So then we go up to the next and we'll slip the next little plate off. Okay, great. Pressure drops, right? And we continue sequentially as the piston rises, as the pressure drops in our blue area, we continue. We're lifting weights. See how we're lifting a weight? So we're doing work, right? And we will have lifted all of our little plates off to state 2. We've gone through a process, 1 to 2. We're going to say that's reversible. Well, how will we reverse it and get back to state 1? Well, what we'll do is we'll slide those plates back on, increasing the pressure, shoving the piston down. We're going to do work on the closed system, And so that would be the claim for the reverse process. This is a classic example of how to build a reversible process. Now, in review, I want to take every opportunity to review jargon with you. This process that we proposed, be sure that you recognize this example is an adiabatic process. So in our example, we had an adiabatic process because I said we fully insulated the piston and cylinder, and I showed it on my sketch, Qn equals 0. Adiabatic process, synonym for no heat transfer. Now what I want to do is step you through the 7 factors that cause a process to be irreversible. 7, so it's going to take a little bit of time. I'm going to step you through the 7 points. The textbook does a good job too, but I like visually seeing things. And so here's my example of reason number 1 for a process being irreversible, and that is heat transfer across a finite temperature difference. In other words, here's my example. I've got a toaster oven, and I'm trying to make a pizza for dinner. Well, I've got this heating coil down here that's red hot. It's at 1,000 degrees or hotter, but probably around 1,000 degrees F, okay? Inside my oven, I've dialed in the desired temperature of my oven to be 400 degrees F. And I'm cooking my delicious pizza, and I'm going to keep cooking it until the pizza reaches an average temperature of about 160 degrees F. That's the serving temperature of a hot pizza as it comes out of the oven. So do you see that this particular process I'm showing is an example of heat transfer from the hot glowing quartz rod into my pizza? That's heat transfer across a finite temperature difference. So in fact, we're going 1,000 to 400 to 160. So numerically, you see, that's a big temperature difference. That process is irreversible. Now let's see if I could propose the reverse process. How do we test if this is irreversible or not with our common sense? Can you imagine? Let's take a plain old room temperature toaster oven. Okay, we open the door up, okay, and we put a pizza in at 160 degrees F. Can you imagine the pizza at 160 F somehow magically getting that quartz rod to become 1,000 F? That would be impossible. So your common sense tells you, my pizza example is a good example of an irreversible process, because you know in your mind that's impossible. The reverse process is impossible. Okay, now we're to number 2. We're at 2 out of 7. Now, this is an extraordinarily important reason for processes being irreversible. Factors which cause processes to be irreversible. Number 2, it's called unrestrained expansion. In other words, expansion, let's say, of a gas where no work is done. We don't get any work out. This is clipped right out of your textbook. I've got a vessel that's got 2 partitions, a partition in it where I've got a closed system of a gas on the left, and I've got a total vacuum on the right. And there's some membrane or something dividing these 2 subsystems. And all of a sudden I bust this membrane. The gas expands to fill the whole rigid tank. Okay, the reason you see that that's unrestrained expansion. I didn't get any work out. It was a rigid tank. I didn't lift a weight, no shaft in there, okay? I didn't do any work. So do you see that in order to get my gas back into half the size of the tank, I've got to do work on that gas, okay? And also I've got to reject some heat because the work would cause the gas to get hotter than it was, okay? And so I would have to reject some heat as well. And so this would clearly be an example of leaving a trace of an effect on the surroundings to get back to where I started from. Irreversible process of doing work and rejecting heat. So this is a classic example of unrestrained expansion. I tried to come up with a real world example, and that would be kind of like popping a balloon. Imagine you've got a balloon. You take a pin, and that balloon contains air at a slightly higher pressure than the surroundings. That's why it's a balloon. So I poke a hole in the balloon with my pen, and kaboom, the gas escapes, right? It expands. It expands from a slightly higher pressure to the atmospheric pressure. I got gas expansion, but I didn't do any work. I was not able to lift a weight. I couldn't capture what that air could have done. Okay. So that's another classic example of unrestrained expansion, popping a balloon. Here's more of an engineering example of unrestrained expansion that you may not have thought of. Here's a real honest to goodness cutaway view of a steam turbine. And I've talked to you about what the turbine does. It's an open system. It takes high pressure steam, and that steam expands, gets a bigger specific volume against these turbine blades. Now, steam turbine engineers are very skilled engineers, and they do their best to design these curved steam turbine blades and gas turbine blades to perfectly extract work from the expanding steam or ideal gas, okay? But it can't, as hard as they try, we cannot do it perfectly. And so there is some measure of unrestrained expansion as our steam is expanding against these turbine blades. And so I hope that helps you understand and get a feel for what unrestrained expansion is in the real world beyond popping a balloon and beyond a piston and cylinder in a lab. Okay, so I hope that helps. Same idea for a pump. So as skilled as our engineers are, they design these impeller blades to compress water from one pressure to a higher pressure. Okay. Thing is that we don't get perfect compression. And so, in fact, at some places within this pumping rotor system, you get pressure that it's increasing. Oops, and all of a sudden, the pressure for some reason drops because of slightly imperfect design. I didn't say poor design, just slightly imperfect design. And so that's also, even in the pumping, the pressure increasing example, a pump has some measure of unrestrained expansion, undesired, unrestrained expansion. We're up to the third out of 7 reasons for processes being irreversible, and that is lost opportunity to do some work. So here's an example of my irreversible process. You've got a 1-ton weight up on a cliff, and somebody kicks it off, shoves it off, and it falls down to earth. Did you lift a weight? No. Did you do any work at all? No. You just slipped it off the cliff. It fell down. You didn't extract any work from that. How could you make that process reversible? Well, here's how you could make that process reversible. If you had a battery, okay, hooked up to, well, a generator, okay. So recognize here, this is not a motor, is it? We would start with our 1-ton weight up here. We would wrap a rope around the shaft of the generator, and then the generator would resist the 1-ton weight just totally falling on its own. So slowly the generator would charge up this battery. In other words, the weight is actually doing work, isn't it, of charging up the battery. Electric energy is a measure of work, right? And so this would be a way. And then once the weight got all the way down to the ground, you'd have a nice charged up battery. So you could flip a switch, turn the generator into an electric motor, and relift the weight. Okay, so reason 3 for irreversible processes: lost opportunity to do work. So I hope that jumps in your mind. The left-hand sketch is an irreversible process. Oh, here's an example of a lost opportunity to do work in the real world. Okay. As I look at this closely, I see this is not Niagara Falls. It is some other falling water at a waterfall somewhere on Earth. And do you see that the potential energy of this water decreases as it goes over the cliff. So the potential energy changes, but the water's not doing any work that it could. So here is an example. Now, this is Smith Mountain Lake, and the Smith Mountain Lake pumped hydroelectric project, where we have Smith Mountain Lake up here. This is Leesville Lake. And there's 200-foot difference between Smith Mountain Lake and Leesville Lake by way of this man-made dam. Okay. There's electric generators that the water runs through during the daytime in order to power, let's say, air conditioners. Okay. And so work is extracted by way of potential energy change. At night, when there's a lower electricity demand, we take electricity off of the grid and run those generators backwards in terms of motors, and we pump the Leesville Lake water back up to Smith Mountain Lake. So this is an example of a nearly reversible process. Hope that helps. Reason 4, direct conversion of work into heat. This one, I think you have a good feel for. So you've been to your circuits class, and you know if you have a battery hooked up to a resistor and you close the circuit, that resistor gets hot, doesn't it? Well, so the resistor rejects heat to the surroundings. So this is an example of an irreversible process, right? And so the idea here is, you notice here the power, the resistor, that's analogous to this very situation too. We talked about it a minute ago, is that since the toaster oven is plugged into the wall, you've got electricity that is the current is passing across this resistive quartz rod, and so it's work turning into heat for a purpose. And then the same idea here. Here's a space heater connected to a 115-volt outlet, just like my toaster oven, and these similar quartz rods are simply heating the house. But this is an example of converting work directly into heat. That's irreversible. Okay, there we go. So here's our observed process on our battery and resistor. Observed process, we're running a current around in a loop. The resistor's getting hot. It's rejecting heat to the surroundings. Now, here's how you know it's impossible to reverse that, isn't it? Imagine heating a resistor. So somehow you're going to heat this resistor up. Is it going to happen that if you heat the resistor up from the surroundings, is the current going to flow backwards and charge up this battery? No, you know that's impossible. So the act of changing work, electric power, into heat is irreversible because you can't visualize the reverse process. You know in your mind that this is impossible. We're up to reason 5. 5 out of 7 reasons for processes being irreversible. And this is a classic. Most students that comes to their mind first. Friction is a phenomenon that is an irreversible process, isn't it? Right? And so thank goodness we have friction, though. Thank goodness we have reversible processes. Many thousands of years ago, folks figured out that if you used friction to rub two pieces of wood together, they'll get so hot that they will burn. Okay, and so here's a great movie example. Let's see, I guess that's Tom Hanks, isn't it? And he was stranded on an island, and he remembered that phenomenon of friction turning into heat. Okay, and so he was able to create fire on his own. Here's an example of a disc rotor, a disc brake rotor that has been run in the lab with the caliper nearly closed, and it is red hot. Okay, and so so a brake on a car, that's a gift, right? So we're praying for friction. When we want to stop the car, we're praying that friction, an irreversible process called friction, is going to bring our car to a halt. So let's imagine in our minds, the reversible disc brake process. What if you heated up what if you heated up a disc brake to red hot and you put it on a test stand, but also then you wrapped a rope around the axle and hooked it up to a weight? You're going to be waiting forever to raise. You know in your mind that there's no way a hot brake rotor is going to start spinning around and pulling a weight up. Okay, doing work, moving a force through a distance. I guess what I didn't say in the previous slide was the how did we get that rotor heated up so hot in the first place? We were clamping down with the caliper and heating it up due to friction. We were doing work. We were spinning the axle with a known torque and speed. Okay, and so what's the point? The point is that friction is a key, a very easy to remember source of irreversibility. 6 of 7. We're coming down the home stretch now. Mixing of materials that can't be unmixed is an example of an irreversible process. And so here's the, well, sweet tea, where we're mixing sugar and Bojangles tea together. But even clearer, here's an example of mixing salt with plain old water. So this is an irreversible process, because on its own, we can't unmix the salt from the water. The salt is dissolved in the water. We can't unmix that. And then typically in class, a sharp student will say, now, wait a minute. We can take seawater and we can turn seawater into potable, drinkable water. So why we're reversing the process? That's a good point. And so here's my answer. You can unmix salt water. So why is mixing irreversible? Here's my answer. So there's 2 ways to unmix seawater. Okay. One is called the reverse osmosis process, where you take a semi-permeable membrane. This is a well-known technology, where you take seawater and push it through this membrane to get fresh water, and you flush the membrane out, and you get very salty water flushing out of the semi-permeable membrane. You say, well, okay, well, that's reversible. Well, it's not, because it takes a lot of pumping work to pump this seawater through the membrane. So it requires work to push the salt water through the membrane. Therefore, you're leaving some markings. You're having the surroundings had to do something. The surroundings had to do some work. That's why it's irreversible. And you say, well, okay. Well, what about the distillation process? And you say, that's a good point too. Another way to change ocean water into drinkable water is to evaporate the salt water. Okay. And what's going to be left behind is the sodium chloride. NaCl will be left in this evaporator, and just H2O is going to come out of the top. Just saturated vapor, H2O is coming out. Okay, but you got steam, but you want to drink it, so you got to condense it, okay, to get your fresh water. So there's 2 things going on here that will be an effect on the surroundings. You've got the boiling process, heat added, and the condensing process, heat rejected in a separate process, clearly irreversible. So I hope that the time spent here helps you get a better understanding of why mixing is irreversible. Now we've come to the 7th and final, for this class, for this course, reason that causes processes to be irreversible, and that is combustion. And so, your common sense tells you this is an example of either natural gas, CH4, or propane, C3H8, where we're adding the fuel, and we're mixing the fuel and air together. We're lighting it off. And what do we get? Well, we get exhaust products and we get heat. So this is a well-known technology. We've known this for a long, long time. That when you mix fuel and air together and light it off, you get exhaust and heat, and you get exhaust products. It makes good common sense that this combustion chamber process would clearly be irreversible, wouldn't it? Well, let's propose it. Well, maybe we can reverse it. How can we reverse this process? Can we make it reversible? Well, here's my proposed process. I've flipped my burner upside down and proposed, well, could we create some kind of process where we inject exhaust products and heat into some magical piece of equipment, and what comes out is fuel on one side and air on the other. Could we do this? And you're going to be able to quantify. It turns out that once you finish this course, you're going to be able to identify that that is impossible. Okay, and so here's my sketch, my reverse process sketch. Exhaust products coming in, you've got some type of unmixing chamber, and what you've got coming out is fuel and air. So this would be an impossible process. Combustion is a classic irreversible process. Well, mercifully, that brings us to the end. I've tried to step you through the 7 reasons for processes being irreversible. Let's see, and early on, I hope that you, as a result of this video, I hope you have sort of a physical feel for types of processes that could be modeled as reversible, and clearly processes that must be modeled as irreversible. 7 reasons why a process is irreversible. Okay, I hope that helps. A classic quiz would be list 4 or 5 out of 7 reasons why a process would be irreversible. It's my hope that you could come up with, so you'd better have at least 2 in your mind. At least 2. Let's see, heat transfer across finite temperature difference. That's going to be 1. A second one is going to be unrestrained expansion. And then you might do a little work before quiz time to think about some of those others. Let's see, lost opportunity to do work. I got that one. How about mixing? That one's easy to remember. Salt going into water, mixing. And then combustion. I think we just got 5 out of 7 right there. So you get the idea. This video can help you prepare for a quiz.